Good still morning, ladies and gentlemen. So this is the only talk about tsunamis I realized, but now I'm the only person standing between you and lunch, so hopefully I keep it short. Let's just move on to the next one. So how does this work? I can't go to the next slide. All right. Okay, so let me start with two videos. This is an amateur video that I think is fascinating and sad at the same time of Tohoku tsunami. What I want you to pay attention, and what's going to be the focus of this talk, is the current that is induced by tsunami. So both the water height and current is much less in the deep ocean. As the waves reach to the shoreline, the speed increases and the height also increases. So the speed of the current in the middle of the ocean is something about 2, 3, 4 centimeters per second. As you can see here, I mean, you can estimate it's probably 10 or tens of meters per second, much higher. But it starts from a real small value and becomes larger and larger. So that's introduction number one. Introduction number two is this aerial photo footage of the tsunami advancing in Japan. Again, sad, but at the same time amazing that we have this video. It's basically showing the wavefront, the run-up of the tsunami toward the shoreline. And the models that we have so far, basically we have a rough estimations of when the tsunami is going to arrive or how much inundation we're going to have. But really the objective of the undertaking I'm going to talk about is to be able to precisely, what we call it in scientific terms, the phase resolve prediction of the tsunami wavefront as it reaches the shoreline. So the measurements that we have in place, one is the dart buoys. These are seabed pressure sensors placed at the bottom of the ocean, and they measure the pressure of if the water surface changes. They send the data using acoustics to a surface buoy, satellite, land. In the normal mode, they send a signal every 15 minutes. In the event mode, they send a signal every 15 seconds to the surface and then relays to land. The issue is, well, first of all, these are very expensive. A single unit costs about $500,000. Regular maintenance is needed, something about $100,000 a year. And total, we have something about 50, 60 units in the world. And also, they are not directional. So they don't tell anything about the direction of propagation. Tsunami is going west to east or east to west. They're very helpful, most reliable technology that we have out there. This is a snapshot of the NOAA webpage that I took a couple of days ago, March 22nd. So 74 stations deployed, 46 reporting in the past 8 hours. So many of them are not reporting. So order of 50 measurements. So this is distributions that we have in the ocean. So the issue, as I said, with the dart buoys are expensive and non-directional. The second technology, I mean, you may think of is the satellite technology. And briefly, I just walk you through the most important stuff that we have here. Why tsunami is not good for the kind of phase results or accurate prediction that I talked about. One is low temporal resolution. So usually satellites have a revisit time of 10 to 21 days. So they rotate about the Earth, but getting back to the same location sometimes takes about, on average, 10 to 21 days. There are satellites with a revisit times of a day or less than a day, but you get the idea, right? This is not good for real-time, accurate prediction of phase resolved, the run-up, and so on. They have a limited real-time capability. The data, I mean, the satellite needs to make a connection with the land-based station, so that doesn't happen in real time. And then usually the data we have a lot of data that needs to be post-processed. So it's just simply too slow for early warning system. They also have a narrow observation path, right? And I mean, you just move on. But starting, the most important one is the low temporal resolution that I just talked about. And then we have HF high-frequency radar, right? So the high-frequency radar, they can have a longer range, something about 100 to 200 kilometers, which is very good, but then the spatial resolution goes down. They have a line of sight limitation, so they can only see things that are, I mean, there's no obstacle, so if there's an offshore structure or ship or just a big wave in front of them, they're not going to see what's going behind that. So as the distance grows, right, the accuracy goes down, and that makes it limited for the kind of prediction we talked about. So the projects that we have, we call it Captain with AI, little bolded because we're going to extensively use large data and AI techniques, is to have these autonomous self-powered sailboats. I mean, self-powered, they use renewable energy, I'll talk about that, and they can stay in water for long duration, a month or years even, right? So a large number of these guys deployed over the continental shelf where the speed is large enough. They make a mesh network, they talk to each other, right? And then they relay the signal to a land-based station wherever we are in San Francisco or LA. And then we're going to do the prediction of exactly what kind of wavefront we expect and how much run-up we're going to get, right? I mean, University Avenue, is it going to be 10th Street and 9th Street? Where exactly the tsunami wavefront is going to reach? So the project has two parts: the software, which is algorithm, how we work with the equations, and the hardware, which is actually, okay, how do we make the boats and what kind of capabilities do they need to have? And it's a big picture talk, so I'm just going to talk about the high-level aspects of kind of both problems that we are, and the challenges that exist in both problems. So precise tsunami profiling and early warning, a network of autonomous self-powered sailboat drones. So just to give you an idea of the rough order of magnitude of where we're going to be and what kind of velocity we're talking about, this community knows much better than me that the top tsunami threats to the United States is from Cascadia subduction zone and then Alaska Aleutian subduction zone. So I'll just go in the next figure to show you. I mean, so this is the Cascadia and then the Alaska Aleutian. So in the next slide, I'm going to show you a very basic simulation, again, just to give you an idea of what we're talking about in terms of tsunami. An earthquake in Prince William Sound that propagates toward Los Angeles. It takes about 7 hours for the tsunami to reach there. Again, very basic simulation. And here I show the time, minute, hours, depth of water. It starts from 110 meters. Speed of tsunami, it starts from 32 meters per second, kilometers an hour, mile per hour, and the distance traveled. So what I want you to pay attention is, well, the speed of propagation using linear theory is proportional to the square root of the water depth. So it's slow, it speeds up, and it slows down. And our idea is to be able to measure the speed where it reaches over the continental shelf, where the speed is large enough that we actually can do the measurements. See if I can run this. There you go. So the speed is low, right? You can look at this, or you can just look here, right? And then it reaches to the deep ocean. The water depth is now 3 kilometers, 4 kilometers. So the speed is relatively large. This is now 2 hours into the tsunami that is propagating from there toward near Los Angeles. And then the speed is pretty stable. 3 kilometers water depth, 650 kilometers an hour. And as it reaches over the continental shelf, which is pretty narrow for the case of California, the speed is going to slow down. So the speed is now going down 100 meters per second. And eventually it reaches to the coast of Los Angeles. So again, the idea is to have the units on the continental, across the continental shelf. So when the speed of propagation slows down, but water, Lagrangian fluid particle speeds up, we are able to measure the speed using the drones that we've devised. And just to be more on the scientific side, this is the kind of velocity we're talking about. So for half a meter tsunami in deep ocean, which is not super small or large, the velocity is about 2 centimeters per second. But then when we get, and this is a time until landfall. So this is 80 minutes, 60 minutes. So this is an hour before the landfall. So something about 35 minutes before the landfall, the velocity is about 10 centimeters per second, and that's basically where we can relatively accurately measure the speed, right? And this is the amplitude. We have different theories. This is based on the so-called Green's theory, linear theory. This is based on the solitary wave theory. So the amplitude probably falls somewhere in between. There is not a universal theory of how the amplitude, how the shoaling happens for the case of a tsunami, which is a more complicated wave than a regular ocean waves. So just briefly about the science, I just point you to the complications that we face. The governing equation is Navier-Stokes, but that's very complex. So we make simplifying assumption. The water is homogeneous, very good assumption for tsunamis. incompressible, inviscid, irrotational. The governing equation becomes Laplace's equation with a bunch of boundary conditions. So this is the simplest ever imaginable partial differential equation in the world. Linear, second order, but that doesn't matter. The complication comes from boundary conditions. So there's eta is the height of water above the mean water surface. There's a time evolution, time derivative. There are nonlinear terms, right? And worse than all, these boundary conditions are written on a surface, on boundaries that are not known a priori. So eta is part of the solution. We don't know where the eta is, right? So that makes the problem very complex, even under these simplifying assumptions that I listed above. So we use typically, if we want to use approximate analytical methods, perturbation method is very useful and handy. So the entire set of equations, if I show it by this nonlinear operator L acting on velocity potential phi, then we assume that perturbation, the velocity potential can be expressed in terms of a perturbation series. It's an assumption. If that's correct, we put it back there. We get a bunch of equations that these equations now can be solved sequentially to basically give us the first order, and then correction, and so on. All right. We also, for direct numerical simulations, there are two methods. I'm just going to talk about one. It's called the higher order spectral method. So it's not a brute force finite volume, so it's a spectral method. It's very efficient for simulating a 10 kilometer by 10 kilometer area relatively easily on a laptop. So, but of course, it has a capability of using parallel computing. So we can take a higher order of nonlinearity into account. We cannot simulate wave breaking, which is extremely nonlinear, but we can simulate pretty steep waves. So what I'm going to just show here a few aspects of the prediction. So the prediction itself is an open problem. We can only measure the surface, either surface height or surface current. But in order to initialize the problem, we need to know what's going on below the surface, right? So this is called reconstruction or inverse problem for the water waves. It's an open problem, right? It's just like looking at someone's face and tell if he has internal infections, right? It's difficult. And then once you do the inverse problem, once you know the phi or velocity below the water surface at t equal to 0, how do you integrate fast in time so that we have prediction? So for 30 minutes, if our computer takes 30 minutes, it's not called predictions, right? So we need to be faster than real time in order to call it prediction. By the way, so I'm going to just point out to a few different aspects of the problem that we looked at, which makes the problem even more complicated than the simple set of equations that I just showed you. So this is for the effect of error on rogue wave prediction. So you can consider this as the maximum run-up that we get from a tsunami. And then because this is computation, we are able to move back, right? And then perturb the initial condition and see how this perturbation evolves over time. So with 10% error in the initial measurement, right, depending on how much time it takes for the wave to reach the coastline, these are basically the errors that we get. So T0, of course, that's the exact one. The 10 TP, which is the peak period, we get something like 13% error, and then 100 TP, 30% and 28%. At some point, it's going to plateau, so it's not going to keep on increasing because it just becomes a regular wave, not a crazy tsunami wave. So the perturbation is going to propagate and affect our prediction of the tsunami. We've also used the convolutional recurrent neural networks, popular today, to do the prediction. It pretty much does, we talk about phase resolve. I really need to know the phase, when exactly I'm going to see the peak in the tsunami wave or the waves that is following or trailing behind. So it was pretty good for the average waves, but for the peak waves, unfortunately, this is under-predicting the maximum inundation, which is I would say, big issue that we still have to resolve. So again, pretty good for most of the waves that we have, but not for the biggest wave in our system, which is something about 15% error, which is relatively large. But there are potentials definitely here. So the previous talk was about landslide. The problem that I've been involved for a number of years was landslide, transient tsunamis. Tsunamis that do not happen far away, and then we have a fully developed waves, but we have very transient situations. So this is a case where we have a landslide going into a lake, right? And then what happens is that these waves start to propagate, but then we have edge waves, and then these waves reflect back, and we can have all sorts of complicated interactions between these waves. I'm just showing you when the problem becomes transient, what kind of things we're going to expect. And one interesting result out of a paper that I want to highlight is the maximum inundation is not the first wave, not the second wave, but it happens somewhere in the middle, right? So landslide goes into water, there are waves moving back and forth, but the maximum runoff or inundation is at a later time, not because of the first wave or second wave, right? It happens at a much later time when these waves reflect back and forth a number of times. Let me briefly, I also talk about this wave interaction with random seabed, because the set of equations that I showed was with a flat seabed. We know that the actual seabed of the ocean is not flat. And that's a phenomenon that in solid-state physics called Anderson localization. Because of randomness, diffusion slows down, or waves slow down, or we can just stop waves, not because of dissipation, but because random scattering. And just a quick result here, that for a solitary wave, which is a model for tsunami, we've shown that, I mean, this is a KdV equation. If the seabed is random, we're going to slow down the velocity. That's proportional to the first term. We're going to have dissipation, and then we have dispersion. So basically what it means is that, well, this is a tsunami without any random seabed. If there is a random seabed, what happens is that the tsunami is going to slow down, not because of dissipation, but because of this Anderson localization. Again, these are the factors that all need to be taken into account in order to address the problem. It's just still an open problem that we're working on. Now, so this is the comments on the software, and then the seabed, of course, is not. I mean, if you have a mud banks on the seabed, that's going to get affected. But in the interest of time, let me also briefly talk about the swarm of boats that we're working on, the sailboats. So we started from a catamaran. So it's very stable, but the issue is if these are going to be long-term in water, if they tip over, they can never be able to recover. So that's why we moved on to a monohull design, and then many different iterations, and there are more futuristic designs we're currently working on. But this is basically the latest version that we have. So there's a sail, there's a wind vane, all electronics, everything inside, and there's a keel to make it balance, and then the bulb keel, and then the keel for going upwind. So this is our kind of production line. We have 7 units working in water. So we just need to make a lot of them so that we can basically do that. For the power, they use 3 modalities. Solar is the trivial one. We have this little hydro generator on the keel. So as these guys sail in water, the hydro generator generates power, so indirectly from wind. So this is a wind power. So this is the hydro generator little here. And then we have the wave power. So if there's no solar radiation and there is no wind, this mechanism, I mean, some of you may remember the old hand self-winding watches. My father had one. So it's basically an imbalanced mass inside the keel. So as the boat rocks back and forth, this imbalanced mass moves back and forth and generates a little extra power to supplement. Because we're doing real-time measurement, we need a lot of power. So the 3 modalities, this is the implementation of the imbalanced mass inside the keel. All right, so this is a little optimization here and there, and the controls. I mean, sailboats are complicated. We have sail, we have rudder, we have the keel, also the coupled set of equations. A lot of electronics involved, the sensors that we have, magnetometer, IMU, the GPS sensor to know where it is. So GPS is really the critical ones to measure the velocity of the current that we want to measure. They make a mesh network. They don't need to. They don't rely on satellite communication. If that becomes cheap and reliable, we'd be happy to directly connect that. So they talk to each other and send a signal to the land. And there's a little app that we've developed so that you can basically tell exactly where each unit needs to go. Yeah, I'm going to keep it quick. So it's been challenging. The environment is always challenging. Arsh is actually sitting there. So there's a seal one day in water trying to tip over the unit. I don't know if you can see this, but this is the seal playing over there. Let's move on from here. Biofouling is a challenge. So we're basically working on the tide. We're very limited, particularly we're doing most of our tests in Berkeley Marina. So we have to basically coordinate it. Obstacle avoidance using ultrasonic sensors. Just watch what's coming at you. We talked to the officials. I mean, there's no concern of boats running into this. The only concern is if they get trapped into the propeller of a boat. Cybersecurity, we have a couple of colleagues interested to work on. And curious people for whatever reason. So the gentleman took the boat out of water, took the UC Berkeley sign off, and just threw the rest at the corner and left. We never understood what the motivation was. But things are complicated, and these guys are pretty innocent, going slowly into water, but you get the idea. Anyway, so the damage was minimal, so we were able to fix it and send it back to water. And yeah, so a couple of other pictures to just see how they work. They rely heavily, entirely on wind power using the sail, and we can just, again, remotely send them the location, and they talk to each other. If one is out of range, the message will be relayed from one unit to the other and to that location. The idea is they're going to be very cheap. It's a concept of swarm, so not a single unit is going to get affected. This is for the landslide case that was talked. So we have this drone carrier. So I mean, the drone gets charged here. It lifts off. It does the measurements from the above. For example, if there's a landslide. This is for lake monitoring that we're doing with Cal State Fresno. So the measurements can be done, and it goes back and tries to land, which is still a challenge. It's been not without accident and incidents, but life goes on. Drones particularly are complicated. All right, and this is a night test, and this is a couple of days ago. 5 units we put in water and send them across the bay. I'm going to stop here and take questions. But thank you very much. This is a work in progress, so well, let's do